Hi gents, today's lesson is on thermal radiation. So we've already looked at conduction and convection, and we're now going to concentrate on radiation. So the lesson objective today, at the end of the lesson, you should be able to explain how thermal energy is transferred through a vacuum, explain what factors affect the amount of thermal radiation emitted and absorbed by an object, and give examples of where we can use this to our advantage. So we've already seen that thermal energy can be transferred via conduction and convection. And in both these cases, that energy is being transferred via particles. In the case of conduction, it's through the collision of particles, one particle gaining kinetic energy, colliding with its neighbour, or via free electrons in the case of metals. But with convection, it is the particles gaining kinetic energy, vibrating more vigorously, moving further apart, and therefore that region of gas or liquid becoming less dense and rising. We can rule these two methods of heat transfer out when we're talking about energy getting from the sun to Earth, because there are no particles in space, and so neither conduction nor convection can therefore take place. So how is that energy getting from the sun to us if it's not being carried by moving particles? Well, the answer is it's being carried by waves. They are electromagnetic waves. Now in year 8 we covered electromagnetic waves in quite a lot of detail, and we will be doing so again in the year 10 course. But for now, I just want you to remember that it is the infrared region of the electromagnetic spectrum that is responsible for the transfer of thermal energy. So because of the fact that electromagnetic radiation can travel through gases and through a vacuum, we now have a valid way of that thermal energy passing through space to get to Earth. Okay, so one of the things we need to look at in our course is the factors that affect the emission and absorption of thermal radiation. The first, the most obvious, is the temperature of the object. The hotter an object is, the more thermal radiation it is going to be emitting. I mean, let's not forget, all objects both emit and absorb thermal radiation, all objects. I mean, the only object that theoretically wouldn't would be an object that is at absolute zero. And as we've discussed in the past, no objects have ever or can ever be at absolute zero. So all objects are going to be both emitting and absorbing thermal radiation simultaneously. If an object is hotter than the room that it's in, or hotter than its surroundings, then it's going to be emitting more thermal radiation than it is absorbing, and therefore the overall effect will be one of emission. If the object is colder than its surroundings, then it's going to be absorbing more thermal radiation than it is emitting, and so it will have an overall effect of absorption. So the temperature of the object in comparison to its surroundings is going to be a very, very important factor when determining the amount of thermal radiation being emitted or absorbed. Okay, the second thing is the surface area of the object. The thermal radiation is being emitted or absorbed from the surface, and so if you've got a greater surface area, you're going to get a greater amount of thermal radiation being emitted or absorbed. And finally, the surface colour and finish of the object. The colour, to be honest, it doesn't really have a significant impact. It's more the finish that has the larger impact on the amount of thermal radiation being emitted. We're going to cut away to some demonstrations now that show this. We're also going to do some practicals on this in our next lesson.
Hi guys, this is a Leslie's cube. It's a metal container that has different surfaces on each face. So the two that I'm going to concentrate on are this one, which is a black matte finish, and this one, which is a white shiny finish. Now what I'm going to do is fill this with water that has been freshly boiled. Now, because each of the faces is made from the same material, we know that the heat is going to be conducted to the surface of each face at the same rate. So if we were to be able to measure the temperature of each face, we'd find that it's exactly the same. all I'm going to do to start with is place my hands either side of the cube, and I can very distinctly feel that this hand, the side that's next to the black matte surface, is significantly warmer than this hand, which is next to the white shiny surface. Now, let's think about how this heat can be getting to my hands. Can it get to my hands via conduction? The answer is no. Why? Because air is a very poor conductor. Remember, the particles in air are very far apart, and so they are unable to transfer heat effectively via conduction. One particle vibrating here is not going to collide with another one vibrating here and pass that energy on. It does happen, but very, very slowly. So we've ruled out the heat getting to my hands via conduction. Can we consider convection? Well, what happens with convection is the air becomes less dense and rises. So would that heat be being transferred laterally? No, it gets transferred in the vertical direction only. And seeing as the heat is getting to my hands in a sideways direction, we can rule out convection. The only way the heat can be getting to my hands is via radiation. Now that's being transferred by infrared waves, which is part of the electromagnetic spectrum. Okay, so what I'm going to do is actually trying to quantify this now. So me holding my hands here and saying, well, this is warmer than this one. Obviously, we're looking at that qualitatively. I want to now look at it quantitatively. So come back to me in a couple of seconds and we'll have a look how we can do that.
So we've just seen from that demonstration that black matte surfaces emit more thermal radiation than white shiny surfaces. We've only done it qualitatively, so I'm saying that I could feel more heat being radiated with the hand next to the black matte surface than I could from the white shiny surface. We'll have a look at it quantitatively in a second, but this is an important demonstration, is one that I would like you to get into your notes. It's really important that we understand what it's telling us. Both of these surfaces must be at the same temperature. The water inside the cube is at the same temperature. Each face is made from the same material, and therefore each face is going to be conducting the thermal energy from the water to the outer surface at the same rate. So we know that both surfaces are at the same temperature. However, one feels hotter than the other. And why is that? It's because of the color and finish. So black matte surfaces emit more thermal radiation than white shiny surfaces. Now let's have a look at it quantitatively.
So we're still with the Leslie's cube. We've already looked at this qualitatively. So I've said that I could feel more heat being emitted from the black matte surface than I could from the white shiny surface. But now I want to look at it quantitatively. What I've done is connected two infrared sensors to our data loggers, and using this this wooden block, I'm going to make sure that they are both equidistant from the surface. That's one of our control variables. Now what we can do is we can have a look at how much heat is being emitted from each surface. The black matte surface is emitting 133.3 watts per meter squared, whereas the white shiny surface is emitting 10.11 watts per meter squared. Clearly, we are having more thermal radiation being emitted from the black matte surface than we are from the white shiny surface, despite the fact that they are at exactly the same temperature.
So we've just seen from that second demonstration that white shiny surfaces definitely emit less thermal radiation than black matte surfaces. So we can actually use some of the content we covered in Year 9 on colour to explain this. Let's think about what a white object is and does. A white object is white because it's reflecting all different colours. Remember, white is a combination of lots of different colours. Now, each of those colours has a different frequency and wavelength within the electromagnetic spectrum. And if a white object is reflecting all those different frequencies and wavelengths, then it's also going to be reflecting the frequencies and wavelengths just outside that visible region. And that's where our infrared radiation lies, just outside our visible region. So if that white object is reflecting all the different frequencies and wavelengths of all the different colours, it's also going to be reflecting the infrared, which is just outside that visible region. Black objects are black because they absorb all the different colours. Remember, black is an absence of colour. So all of the different colours, all those different frequencies and wavelengths have all been absorbed by that surface. It's reflecting none of them. Now, if our black object is absorbing all the different colours, i.e. all those different frequencies and wavelengths within the visible region, it's also going to be absorbing frequencies and wavelengths just outside the visible region. Again, that's where our infrared radiation is. So black objects are going to be absorbing all colours and infrared radiation. Okay, in terms of why the finish, in terms of whether it's matte or shiny, is going to have an impact, we need to think about what we mean by a shiny surface. Now, if you were to look at a shiny surface under a microscope, it would be relatively smooth in comparison to a matte surface, which would be relatively rough. Obviously, to look at, there's not going to be a big difference in terms of roughness or smoothness, but on a microscopic level, a shiny surface is going to be very, very smooth in comparison to a matte surface. Now, why does this make any difference? Well, if you think about the relative surface areas of these, there's going to be a big difference. I mean, they both look roughly the same length, but if I were to take this end of that line and to pull it to the right, I could clearly pull it a long way before it would be perfectly flat. I mean, this bottom line is probably about twice as long as the one on top, and therefore the surface area is going to be twice as large. And actually, because this is I'm not talking about a 1D problem, we're talking about a 3D problem. A matte surface is going to have a significantly larger surface area on a microscopic level than a shiny surface. And remember, one of our factors that affects the amount of thermal radiation being emitted is the surface area. So the larger the surface area, the more infrared radiation is going to be emitted. Okay, so to summarise what we've just seen with the Leslie's cube, black matte surfaces absorb and emit more thermal radiation than white shiny surfaces. It's really important that we have an appreciation for this is both the absorption and emission. Okay, it's not just one or the other, it's both. So black matte surfaces are going to give out, but they're also going to take in more thermal radiation than white shiny surfaces. It's why you would be wise not to wear a black t-shirt on a hot day. On a hot day, if you've got a black t-shirt on, you're going to be absorbing a lot more thermal radiation than if you were wearing a white shiny t-shirt. It's also why you'd be wise to finish your radiators with a matte finish, because you want those radiators to be emitting more thermal radiation. If you make them really, really shiny, they're not going to be emitting a lot of that thermal radiation, and therefore they're going to retain it. If you think about, say, for example, the towel rail in a bathroom, that doesn't give out a lot of thermal radiation. It's very, very hot to touch, and if you place towels on it, it's going to warm them up, but it isn't going to be very good at heating the room because of the fact that it's got that really shiny surface. It's not going to be emitting lots of thermal radiation. The radiators around your house, though they might be white, they are definitely not going to have a really shiny finish because they just wouldn't work as well as they should do in those situations. The other thing to bear in mind is the fact that white shiny surfaces reflect radiant heat more than black matte surfaces. I mean, it's effectively saying the same thing, we're just doing it in a slightly different way. And depending on the question you get asked, you either want to talk about absorption and emission or you want to talk about reflection. But you just need to remember that if something is white and shiny, it's going to reflect lots of thermal radiation rather than absorbing it. So an example of this is a space blanket. So this diagram shows a guy wrapped in a space blanket. So it's like a shiny blanket. You may have seen them being given to people at the end of marathons or being given to hypothermic patients that are stuck on a mountainside. In both cases, what we're doing with this is trying to keep that person warm. I mean, it sounds a bit strange for a marathon runner, but what you don't want at the end of a marathon is for someone to cool down incredibly quickly, because that can then cause issues. So they just wrap them up in it, just so they don't cool down so rapidly. But how do these things work? Well, they do two things. Three things. The first thing is they trap a layer of air. Now, by trapping that layer of air, it stops convection, because the air that is trapped cannot rise, taking the energy away from it. But it also stops conduction, because air is a really poor conductor. Remember, the particles are really far apart, so they're not going to be colliding with each other very regularly, and so they're a very poor conductor. So that trapped layer of air stops both conduction and convection, but the shiny surface also limits heat transfer via radiation. Effectively, all the thermal radiation that's being emitted by the patient or by the runner gets reflected back to them from that space blanket. If the space blanket does actually absorb any of that thermal radiation, because it's white shiny, it's not going to be very good at emitting it. And so again, that blanket is just going to stay warm. It's not going to be emitting lots of thermal radiation. So by using this shiny surface, we can actually really help us to control the amount of thermal radiation being emitted. Two other examples of where the amount of thermal radiation being emitted by a surface is going to be seen is with dirty snow, for one. So the diagram on the left shows some dirty snow on the side of a road, and you'll notice that it's always the dirty snow that melts before the white snow. Why is this? Well, because that white surface is reflecting lots of the radiant heat, whereas the dirty brown surface is going to absorb lots of that thermal radiation. As a result, the brown, dirty, muddy snow is going to melt a lot quicker than the white snow. The picture on the right shows the houses in a very hot country. Why have they all been painted white? Well, they do that for two reasons. First of all, in the day, when it's very, very hot, they do not want their homes to be too hot. So the white finish on the outside is going to reflect lots of thermal radiation. It's not going to absorb very much, and therefore the house should be able to keep quite cool. I mean, it tends to be in hot countries that they get very cold in the evening. And so in the evening, you want that thermal radiation to stay in the house, and again, having a white finish is going to stop lots of thermal radiation being emitted from the house. So it works in two ways. It keeps the houses cool in the day and it keeps them warm in the evening. So in summary, thermal energy is being transferred through gases and vacuums via infrared radiation, which is part of the electromagnetic spectrum. If ever we've got heat being transferred through a vacuum, we now know it must be via thermal radiation, because it can't be conduction, it can't be convection, and it can't be evaporation, because that requires particles. And therefore, if you've got a vacuum, those three methods of heat transfer can't be applicable. It must be via radiation. All objects emit and absorb thermal radiation, all objects. The temperature, surface area, and the colour or finish of an object will affect the amount of thermal radiation being emitted or absorbed. And finally, this has some really positive uses when it comes to insulation. And you need to be able to give some examples and explain why those forms of insulation work better, because they have that shiny surface.